Spring 1945. A secured testing facility outside Munich, Bavaria, Germany. In a parallel timeline that never happened, a Boeing B-29 Superfortress sat intact inside a heavily guarded hangar. Its massive silver fuselage gleamed under industrial lighting. 4 Wright R-3350 engines hung silent beneath wings that stretched 141 feet tip to tip. The tricycle landing gear, radical for its time, held 140,000 pounds of the most advanced bomber ever built. Around it stood Germany's finest aeronautical engineers, technical specialists, and Luftwaffe intelligence officers. They had waited months for this moment. American B-29s had been bombing Japan with devastating effect since mid-1944. Every intelligence report emphasized the aircraft's revolutionary capabilities: pressurized cabin, remote-controlled defensive armament, operational ceiling exceeding 33,000 feet, combat radius of 1,600 miles with a 5-ton bomb load. The Germans needed to understand this machine, needed to evaluate whether their own aviation technology could match it, needed to know if they were truly as far behind as intelligence summaries suggested. What they discovered over the following weeks would shatter every assumption about German technological superiority. The B-29 wasn't just advanced. It represented a paradigm shift in military aviation that Germany couldn't replicate with years of effort and unlimited resources. This is the story of what would have happened if German engineers had captured and tested America's most complex war machine. A story of technological revelation, industrial capacity disparity, and the sobering realization that some gaps cannot be closed through engineering genius alone.
The B-29 program began in 1940 when the United States Army Air Corps requested designs for a long-range, high-altitude heavy bomber. Boeing's proposal won the competition, but what emerged was unlike any aircraft ever conceived. The B-29 Superfortress incorporated over 55,000 individual parts from more than 1,500 suppliers. The nose section alone required 50,000 rivets and 8,000 different components. Total construction demanded 12 tons of aluminum sheeting, 1,000 pounds of copper wiring, 600,000 rivets, and 9 miles of electrical wiring and tubing. Manufacturing proved so complex that Boeing developed an entirely new production system called multi-lining. 6 parallel assembly lines converging into 3 final assembly points. 4 major factories operated simultaneously: 2 Boeing plants in Renton, Washington and Wichita, Kansas, a Bell plant in Marietta, Georgia, and a Martin plant in Bellevue, Nebraska. Thousands of subcontractors across America fed components into this unprecedented industrial network. The development cost exceeded $3 billion, more than the Manhattan Project that created the atomic bomb. Each individual B-29 cost over $600,000 to build, roughly equivalent to $9 million in current currency. But the expense bought revolutionary capabilities. The B-29 featured the first fully pressurized cabin in a production bomber, with separate compartments for the forward crew, rear gunners, and tail gunner, connected by a pressurized crawlway. This pressurization system, building on Boeing's earlier work with the 307 Stratoliner commercial airliner, allowed crews to operate at altitudes exceeding 33,000 feet without oxygen masks or heavy flight suits, a comfort impossible in any other bomber of the era. The defensive armament system represented another technological leap. The remote-controlled turret system, developed by General Electric, allowed gunners to aim and fire weapons from comfortable positions inside the pressurized compartment rather than freezing at open waist guns or cramped turret stations. Gunners controlled turrets remotely using analog fire control computers that compensated for altitude, airspeed, temperature, and bullet drop, extraordinarily advanced for 1944 technology. 10 .5 caliber machine guns protected the bomber from most angles of attack. Early models also mounted a 20mm cannon in the tail turret, although this was later removed due to reliability issues. 4 Wright R3350 duplex Cyclone engines, each producing 2,200 horsepower, provided the power. Twin General Electric turbo superchargers on each engine maintained maximum power up to 30,000 feet altitude. Maximum speed exceeded 350 miles per hour. Service ceiling reached 33,600 feet. Range with a 5,000-pound bomb load extended beyond 3,250 miles. The aircraft featured advanced navigation equipment, precision bomb sights, and, critically, radar systems for navigation and bombing through clouds or darkness. By 1944, the B-29 represented the pinnacle of piston engine bomber design. Nothing in any other nation's arsenal came close.
German aeronautical engineering enjoyed a fearsome reputation in 1944. The Messerschmitt Me-262 jet fighter had just entered limited service. The V-2 rocket demonstrated unprecedented ballistic missile technology. German scientists pioneered swept-wing designs and advanced aerodynamics. But bomber development told a different story. Germany's primary heavy bomber remained the Heinkel He-177, a troubled design plagued by engine fires and mechanical failures. Its coupled engine configuration, 2 engines driving a single propeller, created chronic overheating problems. The aircraft suffered catastrophic losses during operations. The Junkers Ju-390, proposed as a true long-range bomber, never progressed beyond 2 prototypes. The ambitious Messerschmitt Me-264 America bomber, intended to strike New York from European bases, reached only 3 prototypes before cancellation in September 1944. None of these aircraft approached B-29 capabilities. The He-177 could carry 13,200 pounds of bombs, but only for 3,400 miles without payload, with significantly lower operational ceiling and no pressurized crew compartments. The Me-264 existed largely on paper. German strategic bombing remained a fantasy compared to Allied reality. Manufacturing capacity told an even sobering story. By 1944, Allied strategic bombing had systematically destroyed German industrial infrastructure. Factories operated underground in dispersed locations. Skilled workers had been drafted into combat units. Raw materials grew critically scarce. The entire industrial economy functioned in survival mode. Germany simply lacked the industrial capacity to produce something as complex as the B-29. The knowledge might exist, the engineering talent certainly did, but translating designs into mass-produced, operational aircraft required industrial infrastructure Germany no longer possessed.
The hypothetical German evaluation of a captured B-29 would have followed established intelligence procedures. Teams of specialists would systematically document every system, every component, every technical innovation. What they discovered wouldn't have been devastating. The pressurization system. German engineers had experimented with cabin pressurization, but never implemented it in production bombers. The B-29 system maintained comfortable pressure up to 30,000 feet with separate compartments and emergency backup systems. The technical challenge wasn't just building pressure vessels, it was sealing them, maintaining them, and ensuring they could withstand combat damage without catastrophic decompression. The B-29 solved these problems with redundant systems, pressure relief valves, and careful engineering. Replicating this would require new aluminum alloys capable of withstanding pressure cycles, precision machining for airtight seals, reliable pressure pumps and regulation systems, extensive testing to ensure crew safety. Development time, minimum 18 to 24 months. Probability of success, given Germany's 1944 to 45 situation, near zero. The remote-controlled gun turrets represented technological wizardry that German engineers would struggle to comprehend. Each turret connected to a central fire control system using analog computers developed by General Electric, electromechanical calculators that factored altitude, airspeed, temperature, target motion, and ballistic trajectories to aim guns with precision impossible for manual aiming. The system allowed any gunner to control multiple turrets. The upper gunner could fire upper forward, upper aft, or lower aft turrets. Gunners communicated via intercom, coordinating defensive fire against attacks from any angle. German evaluation would reveal over 100 electric motors throughout the aircraft, sophisticated servo mechanisms for turret control, advanced computing mechanisms requiring precision manufacturing, complex electrical systems demanding specialized components. Germany had developed some remote weapon systems, but nothing approaching this sophistication. The Luftwaffe still relied primarily on manned turrets with manual aiming, technology that the B-29 had rendered obsolete. Attempting to duplicate this system would require entirely new electrical infrastructure, precision servo motors Germany couldn't mass produce, analog computing mechanisms beyond German manufacturing capability, months of testing to debug coordination between turrets. Development time, 24 to 36 months minimum. Resource requirements, impossible given wartime constraints. The B-29 carried multiple radar systems: navigation radar for terrain mapping and position finding, bombing radar for striking through clouds, tail warning radar for defensive purposes. German radar technology had advanced significantly, but miniaturization and airborne integration lagged behind Allied capabilities. The B-29's radar units operated reliably at high altitude, consuming minimal power and integrated seamlessly with navigation and bombing systems. German engineers inspecting these systems would recognize immediately that replication required miniaturized vacuum tubes Germany didn't produce, high-frequency generators beyond German manufacturing, integration with fire control systems requiring months of development, extensive testing to ensure reliability. Even if Germany captured complete radar units, duplicating them demanded precision electronics manufacturing capacity that no longer existed. The Wright R-3350 duplex Cyclone represented the absolute pinnacle of piston engine design. Each 18-cylinder twin-row radial engine produced 2,200 horsepower, extraordinary power density for 1944. Twin General Electric turbo superchargers maintained sea-level power up to 30,000 feet. This technology allowed the B-29 to cruise at altitudes where German fighters struggled to operate effectively. German engine development had followed different paths. The BMW 801 and Daimler-Benz DB603 represented excellent engineering, but neither matched the R-3350's power-to-weight ratio or high-altitude performance. Attempting to copy or develop equivalent engines would require new metallurgy for high-stress components, advanced supercharger technology, months of dyno testing to refine performance, solving reliability issues that plagued German high-power engines. Development time, 36 to 48 months. Germany didn't have 36 days, let alone 36 months. Beyond individual systems lay a more fundamental problem: manufacturing complexity. The B-29 required 40,540 different parts and 600,000 rivets per aircraft. The nose section alone needed over 50,000 rivets and 8,000 different parts from over 1,500 suppliers. Building a single B-29 demanded coordination across thousands of suppliers, providing everything from specialized aluminum alloys to precision instruments. The supply chain stretched across America, involving automotive manufacturers, electronics companies, and specialized aerospace contractors. Germany's industrial base couldn't support such complexity. By 1945, German aircraft production had collapsed. Manufacturers were using pressed particle board as aluminum substitutes. Production facilities operated underground, in caves and tunnels, dispersed to avoid bombing. Even if German engineers perfectly understood every B-29 system, they lacked aluminum in sufficient quantities and proper alloys, precision manufacturing equipment destroyed by bombing, skilled labor drafted into combat units, electrical components requiring copper, now critically scarce, and coordination mechanisms to manage complex supply chains. The B-29 didn't just require advanced engineering, it demanded industrial capacity on a scale Germany could no longer muster. History provides one actual example of B-29 reverse engineering, the Soviet Tupolev Tu-4. In 1944, 3 B-29 Superfortresses made emergency landings in Soviet territory after bombing Japanese targets. The Soviets interned the aircraft and crews, then refused American demands for their return. Joseph Stalin ordered Andrei Tupolev to reverse engineer the B-29. The effort involved 900 factories and research institutes across the Soviet Union. Engineers produced 105,000 detailed drawings. The project took 2 years, and the Soviet Union was not simultaneously fighting a losing war on multiple fronts. Even with 3 complete examples, unlimited resources, and no immediate military pressure, the Soviets struggled. Aluminum thickness conversions from imperial to metric measurements forced redesigns. The Soviet Union had to develop entirely new alloys matching American specifications. Engines required complete redesign using Soviet Shvetsov ASH-73 radials since they couldn't duplicate Wright R-3350s. The first Tu-4 flew on May 19, 1947, 3 full years after capturing the original B-29s. Production didn't begin until 1949. The Soviets succeeded because they had 3 complete aircraft to study, intact industrial infrastructure undamaged by strategic bombing, unlimited time and resources, no immediate military pressure, and a willingness to accept weight penalties and performance compromises. Germany in 1945 had none of these advantages. The hypothetical German evaluation report would have made devastating reading for Luftwaffe leadership. Senior engineers would document that the B-29 represented not incremental advancement, but paradigm shift. The aircraft integrated technologies Germany possessed in primitive form, but at levels of sophistication requiring industrial capabilities Germany had lost. The pressurization system alone exceeded German manufacturing capacity. The fire control computers represented electrical engineering beyond current German capability. The radar systems demanded precision electronics Germany couldn't produce. The engines required metallurgy and manufacturing tolerances Germany couldn't maintain under wartime conditions. Most devastating? Even if Germany solved every technical challenge, manufacturing a single B-29 would consume resources equivalent to producing 20 fighters Germany desperately needed for defense. The cost-benefit analysis was brutal. 1 B-29 equals 20 Me-262 jet fighters. 1 B-29 equals 40 FW-190 fighters. 1 B-29 equals resources to keep existing squadrons operational for weeks. and America was producing them by the hundreds.
By the time Germany might have captured a B-29, Allied strategic bombing had created insurmountable asymmetries. Manufacturing the B-29 involved 4 main assembly factories plus thousands of subcontractors. Boeing operated plants at Renton, Washington, and Wichita, Kansas. Bell operated a plant at Marietta, Georgia. Martin operated a plant at Bellevue, Nebraska. These factories operated in complete safety, thousands of miles from enemy action. Workers labored in shifts around the clock. Supply chains functioned normally. Raw materials arrived on schedule. Germany's aircraft industry operated in caves dispersed across the countryside under constant aerial attack. Workers assembled components in underground facilities with inadequate lighting and ventilation. Transportation networks barely functioned. Supply chains had collapsed. The B-29 represented what industrial capacity could achieve when protected from disruption. Germany's situation made such achievements impossible.
History shows how Germany actually responded to superior Allied bomber technology. When Messerschmitt Me-262 jets demonstrated potential to intercept high-flying bombers, the Luftwaffe leadership emphasized fighter production over developing Germany's own strategic bombers. They recognized that defending against Allied bombers took priority over striking Allied targets. German designers proposed ambitious projects: the Arado E-555 flying wing bomber, the Horten HO-18 intercontinental bomber, various America bomber concepts intended to strike New York from European bases. By late 1944, most of these projects existed only on paper. The German aircraft industry had descended into chaos, sundry designs, but totally out of time and resources to resolve problems, debug systems, or produce anything in meaningful numbers. The collapse illustrated a fundamental principle: advanced designs mean nothing without industrial capacity to produce them.
The hypothetical German evaluation of a captured B-29 would have taught lessons Germany couldn't apply. Lesson 1. Integration matters more than individual technologies. The B-29 wasn't revolutionary because of any single innovation. Pressurization, remote turrets, radar, high-altitude engines, other nations had experimented with all these technologies. The B-29's genius lay in integrating them into a reliable, mass-producible system. Germany developed jet fighters, rocket missiles, and swept-wing designs, but they couldn't integrate technologies into coherent, producible weapons systems. The Me-262 entered service too late in insufficient numbers. The V-2 consumed massive resources for minimal strategic effect. Paperwork projects never became operational aircraft. Lesson 2. Industrial capacity trumps engineering genius. German engineers matched or exceeded Allied counterparts in theoretical knowledge, but engineering means nothing without manufacturing capacity to implement designs. America's industrial might, factories operating safely, supply chains functioning normally, millions of trained workers, enabled rapid translation of designs into operational hardware. Germany's shattered industrial base couldn't match this regardless of engineering brilliance. Lesson 3. Complexity requires infrastructure. The B-29's 40,540 different parts and 600,000 rivets demanded industrial infrastructure on a scale only America possessed. Precision components came from automotive manufacturers, electrical systems from electronics specialists, instruments from dedicated suppliers. The supply chain represented decades of industrial development. Germany's industrial base, even before bombing devastated it, lacked this depth. Attempting to build something as complex as the B-29 would have exposed supply chain weaknesses immediately. Interestingly, Germany might have succeeded if they'd pursued different priorities. Instead of attempting to match the B-29's complexity, Germany could have focused on simpler, more producible designs. The Soviets eventually succeeded with the Tu-4, but they had luxuries Germany lacked: time, resources, intact infrastructure. A hypothetical German answer to the B-29 would have required simplified pressurization or none at all, conventional manned turrets instead of remote control, proven engines rather than new high-power designs, reduced range and payload to decrease structural demands, and massive production runs of simpler aircraft. This approach might have produced operational bombers, but by 1944-45, Germany needed fighters desperately. Every resource diverted to bombers weakened air defense against Allied strategic bombing that was systematically destroying German war-making capacity. The strategic situation had evolved beyond the point where German bombers could affect outcomes.
If German engineers had captured and evaluated a B-29 Superfortress in 1945, their report would have concluded: technical evaluation. The B-29 represents the highest achievement of piston engine bomber design. Its integrated systems, pressurization, remote fire control, radar, high-altitude propulsion, demonstrate technological sophistication currently beyond German manufacturing capacity. Replication feasibility. Duplicating the B-29 would require 24 to 36 months minimum development time and industrial resources equivalent to current monthly fighter production. Given current strategic situation, this is impossible. Alternative approaches. Simplified bomber designs might be achievable, but resource allocation to bomber development undermines critical fighter production needed for air defense. Strategic recommendation. Germany cannot match Allied strategic bomber capability. Resources should focus on air defense, specifically high-altitude jet interceptors capable of countering B-29 and other Allied heavy bombers. The report would acknowledge a sobering truth. The gap between German and American aviation technology wasn't about engineering knowledge. It was about industrial capacity, manufacturing infrastructure, and the accumulated advantages of operating in safety while the enemy's industrial base crumbled under sustained attack. The B-29 story illustrates principles extending far beyond World War II aviation. Modern military competition still revolves around not just designing advanced systems, but manufacturing them in meaningful quantities. Having theoretical knowledge of stealth technology means nothing without industrial capacity to produce radar-absorbent materials, precision components, and advanced avionics. The F-35 fighter program faced criticism for complexity and cost, yet it demonstrates American industrial capacity to develop, test, and mass-produce extraordinarily complex systems. Russia and China worked to match these capabilities, but they face challenges similar to Germany's 1945 situation. Theoretical understanding doesn't automatically translate into producible hardware. The B-29 represented American industrial might as much as engineering skill. 4,000 aircraft rolled off production lines between 1943 and 1946. Thousands of suppliers coordinated seamlessly. Quality control maintained standards across multiple factories. The system worked because decades of industrial development had created the infrastructure to make it work. Germany in 1945 couldn't replicate this, not because German engineers lacked talent, not because German industry lacked potential, but because strategic bombing had destroyed the industrial infrastructure that makes complex weapons production possible. Our hypothetical German evaluation of the B-29 would have ended with engineers recommending that Germany abandon strategic bomber development entirely. The industrial capacity didn't exist. The time wasn't available.
The resources couldn't be spared. In reality, Germany never captured a complete operational B-29. The B-29 operated exclusively in the Pacific theater during World War II, never facing Luftwaffe interceptors over Europe. The decision to deploy superfortresses against Japan rather than Germany spared both sides a confrontation that would have dramatically illustrated the technological and industrial gaps between America and Germany. But the Soviets did capture B-29s, and even with unlimited time, resources, and industrial infrastructure intact, they needed 3 years to produce their first copy. Germany in 1945 didn't have 3 years. They barely had 3 months. The B-29 remains a monument to what industrial capacity can achieve. Not just advanced technology, but technology manufactured in quantities that matter. Not just brilliant engineering, but engineering supported by industrial infrastructure deep and robust enough to turn designs into reality. For Germany, examining a captured B-29 would have been like a medieval army inspecting a modern tank. They might understand individual components, they might grasp theoretical principles, but the gulf between understanding and implementation would have been unbridgeable. Some technological gaps cannot be closed through genius alone. They require industrial capacity, manufacturing infrastructure, and accumulated expertise that takes decades to develop and moments to destroy. The B-29 taught that lesson. Germany never had the chance to learn it directly, but the principle remained. In modern warfare, the side that can sustain complex weapons production across extended campaigns wins. America built 3,970 B-29s. Germany captured 0. That simple fact encapsulates the industrial disparity that determined World War II's outcome more than any single battle or technological innovation. The aircraft that never arrived in German hands would have revealed truths German leadership desperately needed to understand: that engineering brilliance without industrial capacity means nothing, that complexity requires infrastructure, and that wars are won not by prototypes, but by production. By the time Germany might have captured a B-29, these lessons came too late. The industrial capacity to apply them had already been destroyed. The war was already lost. The gap was unbridgeable. The B-29 Superfortress, the aircraft Germany never tested, stood as proof that technological sophistication multiplied by industrial capacity equals strategic dominance. A formula America mastered, a formula Germany never had the opportunity to replicate.
In memory of the engineers, workers, and air crews who built and flew the most complex aircraft of World War II, a machine that combined technological innovation with industrial might to help end history's most devastating conflict.